Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Welcome back to the show. You know, I had a bit of a crisis this morning.
Oh, yeah.
I was standing in my kitchen staring at the absolute disaster zone that is my junk drawer. Do you know the one?
Everybody has the drawer, the graveyard of good intentions.
Exactly. It's the drawer where logic goes to die. I had batteries mixed with rubber bands, a screwdriver next to a dried-out marker, and keys to a car I haven't owned in 5 years.
The usual suspects.
The usual. And I decided, today's the day. Today I organize. I went out and bought these little dividers. One specific slot for batteries, one specific slot for writing utensils, one for tools.
So you were imposing order on chaos, a very human thing to do.
I was trying to. But I realized something while I was sorting through this mess. We as humans are obsessed with boxes. We have this biological need to categorize things. Mm-hmm. Is it trash or treasure? Is it edible or poisonous? Is it friend or foe? We have to sort.
It's a cognitive survival mechanism, really. Our brains are processing millions of bits of data every single second.
Right.
If we didn't use shortcuts, if we didn't instantly file things into category A or category B, we'd be paralyzed. We just wouldn't be able to function.
So we crave the binary.
We crave the binary because the binary is safe, it's efficient, it lets us make quick decisions.
Right, it makes the world manageable. But here's the thing that just absolutely blew my mind when I started reading the research for today's conversation.
Okay.
It turns out this obsession with two boxes isn't just a human quirk. For the last 100 years, physicists have been operating under the assumption that the universe itself, the fundamental architecture of reality, is obsessed with two boxes.
You are referring to the categorization of elementary particles.
I am. We've been told that every single particle in existence, from the photons hitting your retina right now to the electrons holding the atoms of your chair together, has to pick a side.
It has to declare its allegiance.
Exactly. You join Club A or you join Club B. There's no middle ground. It's sort of in both.
That is the standard model of quantum mechanics. We call it the great binary. You are either a boson or you are a fermion. And up until very, very recently, that was considered the ironclad law of the three-dimensional world we live in.
But today we are going to smash those boxes.
We're going to see what's in between them.
We are looking at a brand new discovery published literally yesterday, February 3rd, 2026. This comes out of the Okinawa Institute of Science and Technology, OIST, and the University of Oklahoma.
Right.
And what they have found is, it's wild. It's completely wild.
It is a fundamental shift in perspective. It really is.
They've found a way to break the rules.
Yeah.
They've discovered a system where particles aren't just A or B. They can be.
What?
Anything in between.
We are entering the world of anyons. And this isn't just about finding a new particle to add to the zoo, It's not just another entry in the textbook. This is about challenging our very understanding of dimensional space. It forces us to ask, are the laws of physics actually universal? Or are they just side effects of the fact that we happen to live in a room with 3 dimensions?
Okay, let's unpack this, because when I first read the headline, a new class of strange one-dimensional particles, my first thought was, okay, cool, another subatomic speck.
Sure, that's a natural reaction.
But as I got into the text, I realized this is more like finding out that gravity works backwards if you stand on one leg. It changes the context of everything we thought we knew.
That's a fair analogy. And to really understand why this OIST research is so groundbreaking, we have to start with the status quo. We have to understand the prison we've been living in.
The two boxes.
The two boxes. So let's look at our 3D universe. Everything you can touch, see, or interact with, every fundamental particle falls into one of two categories based on how it behaves. Socially, like particle etiquette. You're telling me particles have manners? In a way, yes.
Yeah.
A very, very fundamental way. So let's open the first box. The bosons.
The bosons. Okay, in my notes, I wrote down the conformists, or maybe the party animals.
Both are very accurate. Bosons are the force carriers of the universe. The most famous example is the photon, the particle of light.
Right.
The defining characteristic of a boson is that it loves company. It is profoundly social. If you have a boson in a specific quantum state, that means a specific energy level moving in a specific direction, other bosons are perfectly happy. In fact, they prefer to join it in that exact same state.
They don't mind crowding at all.
They crave it. It's more than just not minding it. The probability of a new boson joining a state actually increases with the number of bosons already in that state.
Oh, wow. So it's like quantum peer pressure.
It is. Hey, all the cool photons are over here. They pile on top of each other, mathematically speaking.
This is the mosh pit particle.
Or a choir. A perfectly synchronized choir. Think of a laser beam. A laser is only possible because photons are bosons. Well, a laser is just trillions upon trillions of photons all marching in perfect lockstep. They have the same color, the same frequency, the same direction, occupying the same space at the same time. They act as a single, coherent wave of light.
And if they were claustrophobic, that wouldn't work. They'd all be pushing each other out of the way.
Exactly. The beam would just diffuse and fall apart. Lasers are a direct macroscopic consequence of this bosonic piling on behavior.
The source material also mentioned Bose-Einstein condensates. That's the extreme version of this, right?
That is the absolute extreme. If you take atoms that behave like bosons, certain isotopes are bosons, and you cool them down to near absolute zero, just a fraction of a degree above the coldest possible temperature,
They basically stop moving.
they slow down so much that their quantum natures overlap and they stop acting like individuals entirely. They collapse into this single quantum state, a superatom.
So you can't tell where one atom ends and the other begins.
You can't. They lose their individual identities and behave as one single entity. It's the ultimate form of collectivism in the universe. It's a truly bizarre state of matter.
Okay, so box one is the bosons.
Yeah.
We are all one crowd. The conformists, the party animals.
The ultimate collectivists.
Now let's look at box two, the fermions.
Ah, the fermions. They are the polar opposites in every conceivable way. If bosons are the force, fermions are the stuff.
Stuff.
The building blocks of matter. We're talking about electrons, protons, neutrons. Everything that has mass and takes up space is made of fermions.
And if bosons are social,
Then fermions are deeply, aggressively antisocial.
they need their personal space.
They demand it. It's not a preference, it's a law.
Mhm.
They obey a rule called the Pauli exclusion principle, and it is arguably the most important rule for our existence.
The strictest rule in the book I read.
It is. It states very simply that no two fermions can occupy the exact same quantum state at the same time. Period.
So if I'm an electron and I'm spinning up in this particular spot with this particular energy,
Then that spot is taken.
no one else is allowed to spin up in this spot.
Correct. You are the sole owner of that quantum state. If another electron tries to squeeze in, it gets repelled. It has to go find a different energy level, a different location, or a different spin. It has to find its own unique address in the universe.
I always thought of exclusion as a negative thing, but the article points out that we actually owe our very lives to this antisocial behavior.
We absolutely do. Our existence is a monument to the stubbornness of fermions.
How so?
Well, think about a simple atom. You have the nucleus in the center and electrons orbiting around it in shells. If electrons were social, like bosons, what would they do? They would all rush to the lowest possible energy state. They'd all pile up right next to the nucleus.
They'd all crash into the center.
The atom would implode. It would be a tiny, dense, and chemically inert little ball. There would be no structure.
And no chemistry.
There would be no chemistry. The reason chemistry exists, the entire beautiful complexity of the periodic table, the reason carbon bonds with 4 things and oxygen bonds with 2, is because the electrons are forced by the exclusion principle to stack up in shells.
It's like filling seats in a theater.
Exactly. Sorry. The first row is full. You have to go to the second row. Second row is full. Up to the balcony with you. That stacking creates different energy levels, and it's the electrons in the outermost partially filled shell that do all the interesting work of forming chemical bonds.
So the fact that my hand doesn't pass through this table, the very concept of solidity,
Is fermions.
is basically because fermions are stubborn introverts who refuse to share a seat.
Precisely. You are pushing against a wall of electrons that are all saying, this spot is taken. Boson attraction gives us forces like light and heat. Fermion repulsion gives us structure and solidity. That fundamental tension is what builds the universe as we know it.
And for a long, long time, we thought that was it. That was the complete menu. You check the box. Boson or fermion.
Yeah.
End of list.
It seemed complete. The math was elegant, and it explained everything we could see and measure in our three-dimensional world.
But why? I love a good rule, but why only two? Why can't we have a particle that's like mostly a loner but likes to hang out on weekends? Why is nature so binary?
That is the exact question that kept physicists up at night. Why are there no others? It seems too simple, almost arbitrary.
It does.
And the answer, strangely enough, isn't really about the particles themselves. It's not an inherent property of an electron that makes it a fermion. It's about the math of how they move. It comes down to a really deep and weird concept called indistinguishability.
Okay, the article used a marble analogy here, and I want to walk through this slowly because usually when people start talking about quantum statistics, my eyes glaze over. But this actually made sense to me.
It's a very helpful visualization. Let's do it. Imagine you have a table in front of you.
Okay.
On that table, you have two marbles. They look absolutely identical. Same size, same glass, same color.
Got it. Two marbles.
In our everyday world, what we call classical physics, you can still tell them apart because you can label them, even if it's just in your mind. You can say, that's the marble on the left and that's the marble on the right.
Sure.
If I were to paint one red and one blue and then I swap their positions, you know I swapped them, it's an observable event.
Right. I see the red one move to the right, blue one to the left. No ambiguity.
Exactly. Even if I don't paint them, you can, in principle, watch them move. You can track their individual paths through space. You can say, marble A went here, marble B went there. They are distinct entities.
Okay, that makes sense. That's our normal intuitive world.
Now, let's shrink down to the quantum level. We have two electrons on our table.
Okay.
First problem. You cannot paint an electron. You cannot put a tiny little sticker on it that says, hello, my name is Electron Bob.
They are fundamentally generic.
They are more than generic. They are indistinguishable. There is no measurement in the universe that can tell one electron from another. They are identical in mass, charge, spin, every single property. They are perfect clones.
So there's no electron on the left and electron on the right. There's just electron.
There is just electronness in two locations. So here's the scenario. You have two electrons. You close your eyes for a second. While your eyes are closed, I swap their positions. You open your eyes. What do you see?
I see. Exactly what I saw before. Two electrons in the same spots.
Precisely. The universe looks identical. The final state is physically indistinguishable from the initial state. But, and this is the absolute core of all quantum weirdness, we describe these particles with a mathematical formula called a wave function.
Right, the thing that describes the probabilities of where it is and what it's doing.
Exactly. And just because the physical scene looks the same doesn't mean the math of the wave function stayed the same. Something can change under the hood.
So an invisible change happened.
An invisible mathematical change. When we swapped two identical particles, the total wave function of the system gets multiplied by a number. Let's call it the exchange factor. It's a phase factor, technically, but exchange factor works just fine.
The exchange factor.
Okay.
So every time they swap, the math gets tweaked by this factor.
Exactly. Now let's complete the operation. Imagine I swapped them again.
So we swap them and then we immediately swap them back.
Right. We've performed two exchanges. Logically, if I swap them twice, everything should be back to exactly where we started, right? Not just physically, but mathematically, too. We've done an operation and then undone it.
Yes. Swap A to B, then B back to A. We are back at the start. No net change.
So mathematically, if we multiplied by the exchange factor once and then multiplied by it again, the final result must be 1, because multiplying by 1 represents no change.
Okay, I'm with you. The exchange factor multiplied by itself, the exchange factor squared must equal 1.
Exactly. So pop quiz. Thinking about all the numbers in the universe, what numbers, when you multiply them by themselves, equal positive 1?
Well, 1. 1 times 1 is 1.
Correct. That's the boson. The exchange factor is plus 1. When you swap two bosons, the wave function doesn't change at all. It's multiplied by 1. We say the wave function is symmetric under exchange.
And, wait, -1 times -1 is also positive 1.
Bingo. That's the fermion. The exchange factor is -1. When you swap two fermions, the wave function flips its sign. It becomes negative what it was before.
Okay, so it inverts.
It inverts. It's anti-symmetric. And that negative sign, that simple minus, is the mathematical root of that entire Pauli exclusion principle we talked about. The math forbids them from being in the same state, because if they were, the wave function would have to be 0, meaning they can't exist there.
Wow, so all of chemistry comes from a minus sign.
In a very real sense, yes. Now, for the critical question, are there any other real numbers that, when squared, give you 1?
No. Just +1 and -1. That's it.
That's it. And that is why the binary exists. The fundamental mathematics of swapping two things in our 3D space forces the exchange factor to be either +1 or -1. There is no room for anything else. The universe's operating system only allows those two options.
It feels so rigid.
Yeah.
It's like finding out that the reason we only have vanilla and chocolate ice cream is because the ice cream machine literally cannot freeze any other flavor. The physics of the machine forbids it.
That's a great way to put it. The machine, our three-dimensional universe, was fundamentally limiting the menu.
And this is the beyond the binary part of our whole conversation. It turns out the machine is only limited if it's a 3D machine.
Correct. This is where the story pivots completely. This is where we break out of the prison.
The source material quotes Professor Thomas Bush from OIST, asking that exact question we posed earlier. Why are there no others? And the answer is, there are others, but they can't exist in 3 dimensions. They need to live in flatland.
Yes. To break the binary, we have to do something that sounds impossible. We have to delete a dimension. We have to go from 3D to 2D.
This is the part I really want to visualize because it's so counterintuitive. Why does flattening the universe suddenly break that strict math rule? Why does x² = 1 stop being the only answer?
It has to do with topology. It's about the geometry of the paths the particles take when they swap.
Okay.
Let's go back to our classical world for a moment. Think about 2 airplanes flying in the sky. That's a 3D space.
Okay, I've got plane A and plane B in my head.
If plane A wants to swap positions with plane B, it has an infinite number of options, right?
Sure.
It can fly over B, under B, to the left, to the right. It can do a huge loop-de-loop and come in from behind. The space is wide open.
Right. Plenty of room to maneuver.
Crucially, because there is so much empty space specifically, that third dimension of height, the paths the planes take never have to get tangled up with each other. You can always find a way to smoothly deform the path plane A took and shrink it down to nothing without ever hitting the path of plane B.
Okay, so their histories, their flight paths, are independent.
In topology, the math of shapes, we say that the swap is trivial. It leaves no lasting trace on the system, and that's the key. Because the swap is trivial, when you do it twice, you have to get back to where you started. The universe forgets the swap happened, which is why the math forces you back to 1.
But now, let's squash the world. Let's take away that third dimension. We are in 2D. We're like 2 coins sliding on a tabletop.
Exactly. Now imagine coin A wants to swap places with coin B. It cannot lift off the table. It has to slide around coin B.
Okay, yeah. It has to skirt around it.
Now it has a choice. Does it go clockwise or does it go counterclockwise?
Does it matter which way it goes?
In 2D, it matters immensely. This is the entire trick. Because you can't lift the coin off the table, you can't just undo that loop you made.
Oh.
Think about it this way. If I walk around you clockwise, holding one end of a rope and you hold the other, and then I walk back to my starting spot, the rope is now wrapped around you once.
Oh, I see. In 3D, I could just lift the rope over your head and it would be untangled. In 2D, the rope is stuck. The tangle is real.
Exactly. The paths get tangled. We call this phenomenon braiding. The world lines of the particles, their paths through space-time, get braided together like strands of hair.
That is such a cool image. The history of the particles movement is a literal braid in space-time.
And because the system is braided, it has a memory. The universe remembers that the particles swap, and it remembers how they swapped clockwise or counterclockwise. And because it remembers, you don't have to go back to the exact starting state when you swap them twice.
So the rule swap plus swap must equal 1 breaks down.
It breaks down completely. The phase factor, that exchange factor, no longer has to be just +1 or -1. It can be any complex number. It can represent a rotation by any angle.
So it can be halfway in between. It can be 10% boson, 90% fermion. It can be...
And any.
Anything goes.
The term was coined by the Nobel laureate Frank Wilczek back in the early 80s. He realized that in 2 dimensions, the rules of quantum statistics could be fundamentally different. You could have particles that were neither bosons nor fermions, but something in between.
So these particles, these anyons, they occupy that vast gray area. They aren't totally social, but they aren't totally antisocial either. They have their own unique set of rules.
They have what's called fractional statistics. Their exchange behavior is a fraction of what you'd see with the normal particles. And this allows for entirely new types of collective behaviors, things that are just flat out impossible in our normal 3D world.
Okay, this sounds like some really out there theoretical physics. Have we actually seen these? Is this real, or is it just a fever dream on a whiteboard?
Oh, it's real. We have. It took about 40 years from the theoretical prediction to the experimental proof, but in 2020, researchers at a lab in France finally observed anyons experimentally.
But wait a minute, we live in 3D. How did they find 2D particles in our 3D world?
They had to build a trap. They had to create an artificial 2D universe. They used very special materials, semiconductors, and cooled them down to near absolute zero, and then applied massive magnetic fields.
So they created extreme conditions.
Very extreme. And those conditions force the electrons in the material to stop moving up and down. They get locked into moving in a strictly two-dimensional layer right at the interface between materials.
Like they're skating on the surface of a frozen pond.
A perfect analogy. And when you confine them like that, when you force them to live in flatland, the electrons stop behaving like fermions. They start acting like anyons. The braiding effect takes over.
Okay, so 2020 was the year of the 2D enyon. We proved the gray area exists. That's a huge deal in itself.
Massive deal. A Nobel-worthy discovery, many would say.
But the paper we are discussing today, this OIST research, this takes it another step further. They're not satisfied with 2D.
No. We are going from flatland to lineland.
One dimension, the ultimate constraint.
This is the work of Jack Featherstone, Raul Hidalgo-Sacoto, and their colleagues. And they asked a very simple but very profound question. What happens if we take away the around entirely?
Right.
1D physics is fascinatingly weird. Let's go back to our analogies. Imagine beads on a string or cars on a one-lane road.
Okay, beads on a string. I'm with you.
In 3D, we fly over. In 2D, we slide around and get braided. In 1D, how do two beads on a string swap places?
They can't. If I'm on the string and you're on the string and I want to get to the other side of you, I'm stuck. Unless I go through you.
Bingo. There is no left or right. There is no up or down. There is only forward or backward. So for particles to swap in a one-dimensional system, they must transmit through one another.
Like ghosts, they just phase through each other.
In a quantum sense, yes, it's a collision, but a quantum collision where they can tunnel through each other. And this interaction, this moment of passing through, is where the brand new discovery lies.
Okay, so what's new about that?
Well, in the 2D case, the behavior of the enyon is usually a fixed property of the material. You buy the semiconductor, you do the experiment, you get the enyon you get, the braiding statistic is locked in.
You can't change the settings.
Right. But in this new 1D proposal, the researchers at OIST and the University of Oklahoma found that the enyonness, where the particle sits on that spectrum between boson and fermion, isn't a fixed property. It depends entirely on that moment of collision.
What about it?
It depends on how strongly the particles interact when they pass through each other.
And can we control that? Can we control how strongly they interact?
We can control it with incredible precision. And this is the magic word from the paper. They call it a tunable exchange factor.
Tunable. Okay, that's the magic word. That sounds important.
It changes everything. It means we aren't just hunting for new particles in the wild anymore. We are building a system where we can literally dial them in. Imagine you have a slider on a mixing board in a recording studio.
Okay, I can picture that.
Slide it all the way to the left. You set the interaction to be very wet. The particles pass through each other easily, almost like they don't see each other. In that case, they act like bosons.
Okay, the social particles.
Now slide it all the way to the right. You crank up the interaction strength. Now when they meet, they bounce off each other hard. They refuse to pass through. They act like fermions.
The antisocial particles.
And the incredible part is the middle. As you move that slider from left to right, as you adjust the interaction strength, you can smoothly transform the particles through every possible shade of any roll.
Wait, really? So you can have a particle that is 37% fermion and then just nudge a dial and make it 38%.
That is exactly what their theoretical model predicts.
It is. It feels like cheating. It feels like we're hacking the source code of reality.
Yeah.
Taking an electron and telling it, no, today you're not going to be an electron. Today you're going to act a bit more like a photon.
Essentially, yes. We are decoupling the identity of the particle from its statistical behavior. The behavior becomes a choice we make in the lab. It's an engineered property of the system, not an innate property of the particle.
This sounds incredibly difficult. So how do they actually do this? You mentioned ultracold atomic systems. Is this something that exists, or is it just a blueprint for a future machine?
The beauty of this paper, and this is why it was published in a journal like Physical Review A, is that it's a recipe. It's a detailed set of instructions for an experiment that can be done with equipment that already exists in labs today.
We already have the kitchen to cook this up.
We do. Labs around the world, including at OST, are experts in this. They use powerful lasers to create something called an optical lattice. It's like an egg carton made of light.
Okay.
And they can shape these laser beams to create arrays of incredibly narrow tubes of light. The tubes are so narrow that the atoms they trap inside can only move forward and backward. They can't move side to side. That's your 1D string.
So they literally build these one-dimensional universes for atoms to live in.
They do. It's routine, which is still amazing to think about.
And the tuning knob, the slider that controls the interaction. How does that work?
For that, they use magnetic fields. There's a wonderful phenomenon in atomic physics called a Feshbach resonance. The details are complex, but the upshot is simple. By tweaking an external magnetic field, you can make the atoms in the trap attract each other or repel each other with almost any strength you want.
So the magnetic field is the slider.
The magnetic field is the slider. You want them to be bosons. Set the field to this value. You want them to be fermions. Set it to that value. You want a very specific type of anion. Dial in the magnet to precisely 2.3 gas, or whatever the number is.
So the theory is solid, the equipment is ready, but here's the big question. How do you know it worked? You can't see an atom with your eyes. You certainly can't see its personality or its quantum statistics.
You watch how they run away. It's a technique called time-of-flight imaging, and the thing they measure is the momentum distribution. Imagine you have your 1D tube full of these ultra-cold atoms. You've set the magnetic field to create your anions. Then suddenly, you turn off the lasers.
The trap disappears.
The trap disappears. The gas, which was tightly confined, is now free to expand.
It explodes outward.
In a very gentle, cold, quantum way, yes. And how it expands tells you everything you need to know.
Okay.
If the particles inside were bosons, they like to clump together. They have a very low relative momentum. So when they expand, they do so in a specific, dense, focused pattern.
Right. The socialites stick together.
If they were fermions, they avoid each other. They have a high relative momentum, so they fly apart much faster, and the cloud spreads out much more broadly.
The introverts run for the exits.
Exactly. And if they are these new 1D anions,
They'll do something in between.
they will produce a specific, unique signature that is somewhere in between. The paper by Hidalgo, Sokoto, and Featherstone essentially gives experimentalists a chart, a field guide. It says, if you tune the magnet to this setting to create this type of anion, and then you release the gas, the spray pattern should look exactly like this.
It's like identifying a bird by its flight pattern because you can't see its feathers.
That's a lovely image, yes. That's precisely it. We can't see the internal state, but we can infer it with incredible accuracy by observing the collective behavior.
So Professor Bush is quoted in the press release saying, this opens the door to improving our understanding of the fundamental properties of the quantum world, which is a very polite, reserved scientist way of saying, this is a big deal.
A very big deal.
But why? Let's bring it back to the listener. Why should we care that we can make atoms act weirdly in a super cold tube? What's the payoff?
The payoff is about control and about a concept called emergence.
Emergence.
Everything we see in the macroscopic world properties like superconductivity, magnetism, the heat capacity of a material, whether something is an insulator or a conductor, all of these things are emergent properties. They emerge from the statistical rules of the trillions of particles that make up the material.
So the little rules dictate the big picture.
The little rules dictate everything. And for all of human history, we've only been able to play with two sets of rules: boson rules and fermion rules. That's it.
We're painting with only two colors.
Exactly. We're trying to paint a masterpiece with just red and blue. But if we can create systems with anions, and not just anions, but tunable anions, we suddenly have the whole color wheel.
Green, purple, orange. All the infinite shades in between.
We can start to ask questions like, what kind of novel material would emerge if its constituent particles had a statistical factor of, say, 0.7? We don't know the answer because nature never gave us a material like that.
But now we can build it.
We can build it. We might discover new phases of matter. We might find new ways to guide energy with perfect efficiency. And the really big one is quantum computing.
Topological quantum computing. I've heard that phrase. It's supposed to be the holy grail.
It is. The idea there is to use that braiding memory we talked about to store quantum information. You encode a bit of data into a knot in space-time.
And because it's a knot, it's stable. You can't just undo it by bumping into it.
Precisely. It's naturally robust against noise from the environment, which is the biggest killer of quantum computers today. This research, by giving us a system where we can directly control the anyonness of particles, is a massive stepping stone toward learning how to create and manipulate those kinds of robust topological states.
So it moves us from just observing nature to actively designing it.
That is a transition we are living through in quantum physics right now. For a century, we were explorers mapping a strange new continent. Now we're becoming architects. We're learning how to build with the quantum bricks and mortar.
It's incredibly exciting, but it also makes you realize how much of our reality, our physical laws, are just local. They're contingent.
They are local to our dimension.
Right. That's the philosophical angle that just gets me. We think the laws of physics are these stone tablets brought down from the mountain. Thou shalt be a fermion.
Thou shalt obey the exclusion principle.
Yes. But it turns out the laws are just suggestions that depend entirely on the geometry of the room you're standing in.
Context is everything. In 3D, the context is rigid. There's too much freedom of movement, so the weirdness gets washed out. In 2D and 1D, the context is constrained, and that constraint allows these new, richer behaviors to emerge.
It's so backwards from how you'd normally think. You'd think more freedom means more possibilities.
But here, less freedom, fewer dimensions means more possibilities for quantum statistics.
So I have to ask, we've talked about going down in dimensions. We went from the rigid 3D world to the braided 2D world to this newly discovered tunable 1D world.
Right. We've gone from 2 choices to infinite fixed choices to infinite tunable choices.
What happens if we go up?
Into the 4th dimension. You mean a 4th spatial dimension.
Yeah. If 3D limited us to just 2 options, does 4D restrict us even more? Or does it open up something totally new that we can't even imagine?
That is a wonderful and a very deep thought experiment. Let's think about the braiding again. That's the key. In 2D, we got onions because the paths got tangled.
Right.
In 3D, we lost the onions because we had that extra dimension to move in, which allowed us to untangle the paths.
The rope could be lifted over the head.
In 4D, you have even more room. You have another direction to move in.
So it's even easier to untangle things.
It's so much easier that it breaks our intuition again. Mathematicians have shown that in 4D space, you can untie any knot in a piece of string without cutting the string.
What? How?
You just lift part of the knot into the 4th direction, pass it under the other strand, and drop it back down. The knot just falls apart.
So 4D is hyper-trivial when it comes to tangles.
Exactly. So following that logic, if we lived in a 4D universe, the rules of particle exchange would likely be even simpler than they are here. The braiding that gives us onions in 2D would be completely gone. You'd almost certainly just have bosons and fermions again.
So the weirdness is a feature of low dimensions.
It seems to be. Or perhaps entirely new structures could emerge that rely on 4D geometry we can't even visualize. Maybe you get new classifications based on hyperrotations. Maybe they have hyperbosons or something even stranger. We don't know.
It completely breaks the brain a little bit. It makes you wonder if there are 4D creatures looking down at our plane of existence, watching us struggle with our bosons and fermions, and just thinking, oh, look at those cute little 3D beings. They're stuck with their binary choices.
Why don't they just rotate into the W-axis to get around that problem? It's so simple.
Exactly. Just sidestep time for a moment. It's easy.
Well, until we figure out how to ascend to the 4th spatial dimension, it seems we have plenty of fascinating new physics to work with down here in 1D.
We certainly do. So, to recap this whole journey today, the universe isn't as black and white, not as binary as we thought.
Not at all.
The boxes we've used for a century, boson and fermion, are real, but they are just the endpoints of a vast, continuous spectrum that only reveals itself when you change the geometry of reality itself.
And thanks to this new research from OIST and the University of Oklahoma, we now have a theoretical map and an experimental recipe to access that entire spectrum. We can finally turn the knob.
It's a great reminder that when you're organizing your life or, the universe, sometimes the problem isn't the stuff you're sorting, it's the boxes you're trying to force them into.
Or maybe it's just the dimension of the drawer.
I am definitely blaming the topology of my kitchen drawer for the mess next time.
Yeah.
It's not my fault, honey. It's the non-trivial braiding of the spatulas.
Good luck explaining that to your guests. I'm sure it will go over well.
I'll give it a try. Thank you so much for walking us through this. This was a heavy one, but I really feel like I get it now.
It was a pleasure. It's always good to stretch the mind a bit, and this topic certainly does that.
And to everyone listening, thanks for sticking with us as we went down this rabbit hole. Keep questioning the categories, keep looking for the gray areas, and remember, the laws of physics might just be waiting for you to change your perspective.
Be curious.
We'll see you on the next one.